Welcome back to the Jerusalem Science Contest. This week is Chapter 5 in your book, which is the chapter entitled Interactions of Ionizing Radiation with Matter, which begins on page 77. And this is, of course, the fifth lecture. So today what I'd like to talk to you about, which is a very, very important topic, is exactly how the kinds of radiation that we've been discussing through the last four chapters, we've learned about their energy, but one of the things that we haven't learned is actually how they interact when they collide, when these particles, or in some cases photons, actually wind up colliding with matter. So we're going to find out that if we're dealing with particulate radiation, there's going to be one set of things that's going to occur, and if we're going to be dealing with photonic radiation, there'll be another set of things that are going to occur. So we're going to start out with the particulate forms of radiation, and principally alpha radiation and beta radiation. So we'll begin, as I said, on page 77. And again, ionizing radiation is going to be any form of radiation, whether it is particulate or photonic, that's actually going to cause atoms to ionize. That is, that they're going to lose electrons. So they're going to have to be, in order for that to happen, there's going to have to be a certain amount of energy that's going to have to be absorbed by the atom in order to actually kick an electron. And it's usually an outer shell electron that's going to be actually booted out, and that's going to require that the incoming particle or photon has a particular amount of energy. Because as we've seen before, if we have a photon that is weakly energetic, it's not going to be enough to actually cause ejection of the electron, of an orbital electron, but it might just promote that electron to a higher energy level. So we've seen that, for instance, with things like ultraviolet light. If we have UV light, we're going to get an increase in fluorescence, which is because the electrons are being promoted to a higher energy level. As they fall back down to the ground state, they're going to emit a secondary photon, which is going to be of a lower energy, but we're not actually going to lose an electron. So in classical mechanics, we would say the kinetic energy is equal to 1/2 mv squared. The energy of whether it's a particle, well, in this case we're actually dealing with particles because we're dealing with something that has mass. Photons are massless, so we don't actually consider them for this. But if we're dealing with a particle, we can say, at least in the classical sense, that is when we're dealing with particles that are not moving very close to the velocity of light or of electromagnetic radiation, that in that case we can apply this equation 1/2 mv squared, and that will give us the energy. And from that we could actually calculate the velocity. So the velocity would be 2 times the kinetic energy divided by the mass. The square root of that would actually give us the velocities. I just rearranged the equation. So that's something that we could actually find the velocity of a particle if we knew its kinetic energy, and if we knew its mass, it would be the square root of twice its kinetic energy divided by its mass. This is something that's interesting, and it's useful to know. So when particles are going to be colliding with other particles, there's 2 kinds of collisions we can have. We can have what's called an elastic collision, where fundamentally all the incoming particle, let's assume one of the particles is stationary, and there's another particle that's going to collide with it, and when that particle hits the first particle, all of the energy that's in there is actually going to be conserved. One particle will transfer its energy to the other particle. If the incoming particle is a very, very large particle, it's going to what's actually being conserved here is momentum. So the mass times the velocity of the first particle is going to equal the mass times the velocity of the second particle. So if you've got a really massive particle incoming with a high velocity, what's going to happen is or even if it's not a very massive particle and it hits another particle, if its velocity is high and the other particle, let's say maybe has 1/4 of the mass, it's still going to eject the lighter particle since it came in at a high velocity. The lighter particle, if the lighter particle is the particle that's being hit and it's 1/4 of the mass, we'd expect it to have 4 times the velocity when it's actually ejected. If there's if the momentum is being conserved and it's an elastic collision. So we have that one kind of collision, and there's another kind of a collision which is called an inelastic collision. And in that case, where we've got an inelastic collision, we're going to have something else happening where we're actually going to find that energy is going to be lost, or it's not going to be transferred in the same way. So some of the energy may actually be used to cause something else to happen. It's not just going to be this simple kind of I've got one particle that's striking another particle, and then this particle maybe stops or it continues to move at a slow rate and this other particle ejects. There's going to be something else that's going to be taking place. So we'll look at that momentarily, what happens in inelastic collisions. But I want to start out first of all with the alpha particle and what kind of collisions we might expect from that. So an elastic collision is where kinetic energy of the particle is cleanly transferred as kinetic energy to the electron. That's what we're actually dealing with. We're dealing with a particle, and in this case a very, very large particle, if it's an alpha particle, that's hitting an electron, and it's going to transfer the energy to the electron. And as you might expect, assuming that the energy is great enough, we could actually knock the energy of the incoming alpha particle is great enough, we ought to be able to knock that electron right out of its orbital. So if you look at figure 5.1 on page 78, you'll see in one case we've got an incoming, this might be for instance a photon that's coming in, and we've got an electron in the ground state, and it's being promoted to an electron in an excited state. And in that case, that's what I was talking about when I said fluorescence. That could be say a UV photon. The electron is promoted from here up to here. Here's the nucleus. Here's the electron. It gets promoted up to here. It's an excited state. It falls back down. It emits a photon. So that's not what we're talking about here when we talk about formation of ions, which is what since we're talking about ionizing radiation. What has to happen in that case is that this electron, rather than just being promoted to a higher energy level, it's got to be ejected. And at that point, we form something called an ion pair. So we have the electron out here. It's actually removed from the atom. And now we've got an atom that is going to become an ion. It's going to have a net positive charge in it, because if all the charges were neutralized, when we lose one electron, then there's going to be one excess positive charge. And this is what we refer to as an ion pair. And then there's also the possibility that this electron here, which is being ejected, now will interact with other atoms, and it will produce secondary ionizations. And these secondary ionizations are then going to catalyze not catalyze, but cause emission of more of these electrons. And a long time ago, early researchers in the early part of the late part of the 19th century, the early part of the 20th century, thought that they had detected a new kind of radiation outside of gamma radiation. They thought they had a new kind of radiation, which they called delta radiation. And delta rays are nothing more than, was later found out, are nothing more than these secondary electron beams that are being caused by the secondary electrons. All those together constitute what were then called delta rays. But these are not really rays per se. They're just this just a secondary electron scattering. Okay, so we've got excitation and ionization, and there's an example given on page 79 where they're trying to show you, let's see, you've got an alpha particle that's being emitted by polonium, and you know what shell it's coming from, and if the alpha particle has it's a 7.6868 million electron volt alpha particle. But the alpha particle, after it's reacted, has lost some of its energy, and now it's only 7.6830 million electron volts. So the question is, will the electron be removed from the polonium atom? So you have to subtract this new energy that the alpha particle has after this, which is the 7.6830 MeVs, from the original 7.6868 MeVs, and you get a difference of 0.0038 MeVs, which is 3.8 kiloelectron volts. And then you have to look at that and then determine, which you can do. You can look this up, or it's actually shown in the book, that the binding energy of an M shell electron in holmium, which is what we're looking at to see whether it's going to be ejected, is 1.7 kiloelectron volts, and the difference between 3.8 and minus 1.71 keVs is 2.1 keVs. So it's telling us that because it's only 1.71 keVs and we have 3.8 keVs of energy there, that in fact this will be ejected. We are going to get ionization occurring, and there's actually an excess. The freed electron then is going. The energy of that is going to be equal to the difference between the 3.8 kevs and the 1.71 kevs, approximately 2.1 kiloelectron volts. And from that, we could also go back using the formula here, K equals 1/2 mv squared. We could go back from that, and we could actually calculate the velocity, as I've done here. And they do that on page 80. If you look on page 80, you'll see where that is actually being done. And you have to do a little bit of conversions here, because you have to convert from, you can't use MEVs or KEVs. You have to convert those back into joules, because when we're using K equals 1/2 mv squared, the kinetic energy, we want to show that in joules, because joules have the units of kilogram meters squared per second squared, and we're trying to get a velocity which is going to be in meters per second. So in order to do that, we've got a mass. Kilograms are going to cancel out, and we're going to have the square root of m squared over s squared, which is going to be meters per second. We're going to get an answer that's going to be in meters per second. It's going to be a velocity. So we do the conversion down on the bottom of page 79, and you can see that 7.6868 million electron volts for this problem, the previous problem that I was mentioning, actually converts to 1.231 times 10 to the minus 12th joules, a small amount of energy. And if we then substitute that into the equation that I've derived here, you'll find out that you're going to find out that the velocity, once you do this, is going to be equal to 1.925 times 10 to the 7th meters per second. Which the author makes the point that that's fast, but he doesn't really tell you, or you're not really looking at, if you look at this value, 1.925 times 10 to the 7th meters per second. What you really want to compare that with is the velocity of a photon, and a photon is going to be traveling at the 3.00 times 10 to the 8th meters per second. So we could actually find something which is called V over C, the velocity of this compared to the velocity of that, and you'd find out that if we did that this is only a small fraction. It's something like, I don't remember what it is, maybe 6% of the velocity of light. So this particle, this alpha particle, really is not traveling. It's traveling rapidly, but it's certainly not traveling anywhere near the velocity of light. Now, the other thing that we need to take into consideration is that as we get up to these higher and higher velocities, we can't necessarily assume that the classical equation is going to be valid anymore. So at some velocity, there's going to be a difference, and we can actually calculate this, there's going to be a difference between the values that we're going to get using the classical equation and an equation that is actually corrected for relativistic effects. That is, as we start to approach the velocity of light, there's going to be relativistic effects that are going to actually change the kinetic energy. And we're going to find that the closer we get to the velocity of light, the higher the kinetic energy is going to become very, very rapidly. So we actually have another equation in here. I'm going to erase this. We'll put the other equation down here. And the other equation, I hope everybody will be able to see this. We had some problems last week. I tried to change the lighting in here because I've lowered the lighting intensity a lot. So it's a little bit harder for me to see, but hopefully it'll be easier for you to see the board. There was a lot of back reflection on the board, making it difficult to see. So we have an equation, it's actually equation 5.2 on page 80, and it says the kinetic energy is equal to, and it's got in parenthesis now, it's got a quantity which is 1 over the square root of 1 minus v squared over c squared minus 1, this entire thing, times mc squared. So it's no longer kinetic energy equals 1/2 mv squared. It's now got this particular term in here, and it's the reciprocal of 1 over the square root of 1 minus v squared over c squared. This quantity, 1 over 1 minus v squared divided by c squared, actually has a, it's got a symbol that is sometimes used to represent it, which is gamma. So gamma equals 1 over the square root of 1 minus v squared over c squared. And it is this correction term that's put in here, which is called the Lorentz factor. And the Lorentz factor actually corrects or changes this equation to take into consideration velocities that start to approach where v starts to approach c. Now, one thing that you might notice, which could cause a little bit of consternation, is that when v actually equals c, what you've got then is v equaling c, then this becomes, these two terms become equal to 1, and then you've got 1 minus 1, and that's going to give you 0 in the denominator. So you're going to have 1 over 0 minus 1, and that's very unsettling because that 1 over 0 term is actually something that ought to be infinite. The thing that maybe makes it a little bit easier to see is that you can't really ever actually hit c if you actually have mass. So for a photon, c and these two terms would actually be equal to one another. But if you're dealing with a particle, something that has mass, you could get up to velocities that are going to be 90-some% the speed of light, but you're never actually going to hit the speed of light for a particle that actually has mass. Although you know, now there was an experiment done at CERN probably a couple months ago, which still has not been actually confirmed, where it seems like some tau neutrinos might actually have superluminal velocities. Let's say they may have velocities that actually exceed the speed of light. But these are very, very lightweight particles, and as I said, those results haven't been confirmed. And if that turns out to be the case, we're going to have to modify, some of these equations are going to have to be modified in order to take that into consideration. But these equations seem to work very well to actually give us an idea of what the kinetic energies of these things are. So in that case, what would actually happen, since m is equal to 0, the kinetic energy, we really don't have to worry about those particular terms. And again, where v is equal to 0, in that case where the particle is not moving at all, then this just becomes, kinetic energy of course becomes equal to 0, because you've got 1 minus 1 times mc squared. It's, the whole thing is equal to 0 anyway. But you know, even if the particle actually has mass. So somewhere in between, we're going to get these values, somewhere in between something not moving at all and something moving as it's starting to approach the velocity of light. There's going to be values, these values are going to change, and basically the author is making the point that you actually have to try to apply these formulas. This formula is actually, so you could write this in a simplified form and just say that the kinetic energy is equal to gamma minus 1 times mc squared. That's just a kind of simplified way of writing that, but you need to know that gamma is 1 minus the square root of 1 minus v squared over c squared. And in any event, you can also rearrange this. The author says it's not trivial. I thought it was trivial. It actually took me quite a while to do the math to rearrange it, but I did derive the same formula that he has in the book, and so I know that that is correct, that v, the velocity, is going to be equal to c times this factor. This is now rearranged to take into consideration the Lorentz factor, so it now becomes 1 minus mc squared in the numerator divided by Ke, kinetic energy, plus mc squared, and that entire term in here under the square root sign is squared. So it's 1 minus mc squared over Ke plus mc squared, that quantity squared. And if you go through all of the hairy math in here, you find out that it has a velocity of, the velocity is equal to 1.922 times 10 to the 7th meters per second. In the previous problem, where we just used the simple kinetic energy equals 1/2 mv squared, we got a velocity equal to 1.925 times 10 to the 7th meters per second. So it's not an enormous difference here. It's 0.003 times 10 to the 7th meters per second, which is 3 times 10 to the 4th, but it still enables us to get a closer value. And if that thing were moving closer to the speed of light, then we would have gotten an even bigger difference between these two values. Okay, so that's just something. I'm not going to ask you anything like that on the exam. It's too much math, and you don't really need to. But you should understand actually how to do those kinds of things, and you can see that there is a difference. Now there's something else that he shows, which is just V over C. So V over C is just going to be, if you wanted to calculate this quantity V over C, you're just going to multiply both sides of the equation, divide both sides of the equation by C. So you're going to get V over C equals the square root of 1 minus mc squared, etc., etc., and that is shown as equation 5.4, which is just a way of rewriting equation 5.3. We're going to see that V over C is going to be a term that we're going to use later on, so you might want to just keep that in mind. Okay, let's see. The other thing that's very important on this page, on page 81, is the idea of something called linear energy transfer. And there's two new terms that we have to introduce. One of them is called the W value. Your book calls it the W quantity. It's usually referred to as just W or W value. But the W value is actually the average energy that's needed to produce an ion pair. So, for any of these kinds of collisions that involve whether it's an alpha particle or a beta particle that are actually colliding with an atom and with an electron of that atom and causing it to ionize, the question is, or what we're talking about when we talk about the W quantity, is the actual amount of energy on average that is necessary in order to cause that atom to ionize. So that's W. And then there's another factor that we need to know, which is called the specific ionization. And this is going to vary from particle to particle. Not only it's going to depend not only on the energy of the particle, but the type of particle that we're dealing with. So the specific ionization for alpha, and it's not just particles that do this, by the way, it's also electromagnetic radiation. So the specific ionization for an alpha particle is going to be different than the specific ionization for a beta particle. That's going to be different than the specific ionization for a gamma photon or an X-ray photon, for instance. Okay, so let me clear this. And the other term, so I didn't mention that I said these things were different, but what is the specific ionization? It's actually the specific ionization is going to be the number of ions or ion pairs that are produced per unit path length, and we usually use as the unit path length. We tend to use the centimeter for that value. So it will be actually the number of ions that we're going to be producing per centimeter that the particle is actually traveling. So we then have something called the linear energy transfer. Linear energy transfer. And this is nothing more than the product of those two terms. So it's W times the specific ionization. So we take the W, the LET, the linear energy transfer, is equal to W times the specific ionization. And we can do some stuff with that. We can, I think there's probably so on page 82, we've got an example, an alpha particle of a certain energy. Alpha particles of a certain energy have a specific ionization of 5.05 times 10 to the 6 ion pairs per meter. And we're calculating the LET value for these particles in air. And we write down that there's 5.05 times 10 to the 6 ion pairs per meter times 33.85 electron volts per ion pair, and we get a value of, once we multiply that out, we get a value of 1.71 times 10 to the 8th electron volts per meter, 171 million electron volts per meter. So that gives us the linear energy transfer. Okay, and then there's something else called the range, and the range is actually the energy of the particle divided by the linear energy transfer. So what that's going to tell us is how far that particle is actually going to wind up moving in a specific medium. So in this case, well, here's a different example. It's americium-241. This is the stuff that you find in your smoke detectors. So you know the way that a smoke detector works is that the americium is producing alpha particles, and the alpha particles are reacting with gas that's inside the chamber, and they're causing these ionizations to occur. Now what happens when smoke gets in the chamber, so there's always like a certain amount of current that's actually flowing into the device, into the detector of this, into the smoke detector chamber. So when smoke actually gets in there, the smoke starts to intercept these particles, and the amount of ionization that you're getting in there starts to fall off, and that signals the alarm. So the device is actually reading, I guess, a lower current, and that signals the alarm. The alarm goes off. So in this case, we're looking at this americium using the smoke detectors. One of the reasons it's used is because the LET of air is significantly lower than the LET of smoky air. So that's what I was referring to before, that the linear energy transfer in air is much less than it is in smoky air, because smoky air is going to absorb a lot of that energy. So we're calculating the linear energy transfer and the range of a 5.4857 million electron volt alpha particle that's emitted by americium-241. And the specific ionization is given here as 3.4 times 10 to the 4th ion pairs per centimeter. And so we write that down. We multiply that by 33.85 electron volts per ion pair. This is right below equation 5.6 on page 82. So we're going to use the formula there. Range equals R equals energy divided by linear energy transfer. And what we're going to find is, first, as I said, we're calculating linear energy transfer. That's LET. The LET value is the 3.4 times 10 to the 4th ion pairs per centimeter times 33.85 electron volts per ion pair times a million electron volts is 10 to the 6 electron volts, and that's going to give us a value of ion pairs will cancel out, electron volts are going to cancel out, and that's going to give us a value of 1.2 times, I'm sorry, 1.2 MeV, million electron volts per centimeter. And then we can take that value and substitute it into this equation here. So we're going to have the 1.2 MeV per centimeter as the LET, and the energy we already said was 5.4857 MeVs, and when we divide that out, we're going to find out that that's going to come out to, the MeVs are going to cancel out, and we've got the reciprocal of reciprocal centimeters, which is centimeters, and it comes out to 4.8 centimeters. That's about 4.8 centimeters is about 2 inches. And that's about how far you're going to expect an alpha particle to be able to move before it's going to be, before it's actually going to be trapped, before it's going to hit something. So these alpha particles are completely stopped by only 4.8 centimeters of air. Now the smoke detector, in the smoke detector, they're not, that's just if it was clean air. In the smoke detector, they're not even going to get that far. Okay, so let's see, what else do we have in here? Oh, on page 53, then we want to, so that gives us our range, by the way. That value that we just calculated, that is the range of the alpha particle would be 4.8 centimeters. And you could do that for other particles as well. And you would find out, or for photons. So you would find out that alpha particles have the highest specific ionization, but the lowest range of the particles. Betas are going to have a lower specific ionization, but they're going to have a greater range. And things like gamma or X-rays are going to have an even lower specific ionization, but their range will be much greater. So these are good things to know.